Hello, and welcome to designing a flyback DC to DC converter. In this video, we will finalize the schematic design procedure by selecting the other external components. My name is Brigitte Hauke. I am Boost and Buck Boost Controller Application Manager in Texas Instruments. This video is the fourth one of a video series which concentrates on the flyback converter design and gives some guidance for practical issues. So let's go on with the design procedure of a flyback converter. I demonstrated on the controller IC LM5155, but most information is generic. We recommend these 9 steps for the converter design. In video 3 of this series, we discussed the first 4 steps of the design procedure. In this video, we will concentrate on selecting the other components of the power stage, closing the loop, and other external components. The PCB design will be discussed in video 5, together with some more details of the transformer. So let's go on with the design procedure. After the transformer, the most important component is the MOSFET. The steady-state analysis determined the parameters we need for the MOSFET. These have been determined in video 2 of the series. The primary RMS current is used to calculate the conduction losses. The drain-to-source voltage, which is the maximum input voltage plus the reflected output voltage, gives the minimum voltage rating. To have enough margin, I recommend choosing a MOSFET that has more than 1.5 times the voltage rating of the calculated VDS. Select some FETs that seem to fit the voltage and current rating and calculate the conducting and switching losses based on the datasheet parameters and these formulas. Remember using 1.5 or 2 times the RDS-on value in the datasheet for calculating the conduction losses, because the MOSFET will heat up and possibly the drive voltage used is different. I added this factor into the formula for conduction losses. In this case, 1.8 times is used. In the table, you can see the results for 3 different MOSFETs from Texas Instruments. The 2 green boxes show that the MOSFET with the lowest RDS-on is not the one that has the lowest overall losses. This is often the case and valid for almost all types of converters. And this is often a reason for some iterations to finalize the converter design. MOSFET losses are hard to predict, so I recommend testing different MOSFETs in the lab, or at least having different MOSFETs in the same package available if needed. In the design, I would as well place a gate resistor from the gate driver output to the gate pin of the MOSFET, just in case it is needed. Especially during EMI testing of the flyback, it might be necessary to reduce the rise time of the switch, and these tests are often done late in the design, so PCB changes might be painful. For every flyback converter, I recommend placing the components for a snubber across the primary winding. It might not be necessary, but if needed, it is good to have the footprints available on the PCB. After the design of the transformer is finalized, normally the RCD clamp is used as it is lower in cost, but for the first test I recommend using the DZ plus D type. The DZ plus D snubber is independent of transformer parasitics, so it can be selected using these 2 formulas. The snubber works good, but might be somewhat expensive, and due to cost reasons, exchanging it with an RCD clamp might be necessary. For detailed snubber design, have a look at the application note Snubber Circuits Theory, Design and Application from Philip C. Todd. Although it is not new, it is still very interesting to go through. The next step is the selection of the secondary side rectifier diode. In the steady-state analysis in video 2 of the series, we calculated the peak inverse voltage of the diode to 23 volts. As we want to have some margin, I recommend using a diode with a voltage rating of at least 1.5 times the PIV. So a 40-volt diode is a good choice. The rated current has to be greater than the output current. If we estimate the power dissipation with roughly 0.7 volt times the output current, we know that a certain size of package is necessary to dissipate the power. Yes, Schottky diodes have lower forward voltages, but a lot bigger capacitance, which causes losses as well, so the estimate is valid even for these. So for power dissipation reasons, a diode in the TO277 package is a good choice. As well as on the primary side, we recommend reserving the space for snubber components across the rectifier diode. I place normally an RC snubber with a resistor in a package that can dissipate something like 0.5 to 1 watt. Now let's go on with selecting the right current sense resistor. The LM5155 is a peak current mode controller, so the sense resistor needs to be selected that it does not trigger current limit at full load and lowest input voltage. And it has to protect the transformer from going into saturation. So it has to be smaller than 27 milliohm and bigger than 17 milliohm. So 20 milliohm was chosen for this design. As the power dissipation is in the range of 70 milliwatt, a resistor that can dissipate 1/8 of a watt seems to be sufficient. But to have enough margin, I use a 1206 non-inductive resistor that can dissipate 1/4 of a watt. As inductance and capacitance of a resistor are heavily dependent on the distance of the terminals, I recommend using a resistor that has the terminals on the long edges as indicated by the pictures on the bottom right. The parasitics of the MOSFET and the traces will cause a leading edge spike whenever it turns on. LM5155 has some leading edge blanking, but as it might not be enough for the specific flyback design, adding filter components to the CS pin is recommended. The RC time constant should not be above 3% of the switching cycle to avoid distortion as shown as dashed blue lines in the CS pin voltage at the bottom. Keep in mind that the controller is blind for overcurrent while the filter capacitor is charged. The output capacitor serves two purposes. It keeps the output voltage stable when no energy is delivered from the input in every switching cycle, so it needs to be big enough to make sure the ripple does not get too big in steady state. Often 1% is the maximum for this ripple voltage. So for this design, the output capacitance needs to be higher than 250 microfarad. A second purpose is to make sure that the output voltage does not undershoot too much when the load increases and does not overshoot too much when the load decreases. This voltage change is called load response. The load response is often specified with 2 to 5% of the rated output voltage. It is dependent on the crossover frequency of the converter. For a flyback converter, it is good design practice to keep the crossover frequency at or below 1/5 of the frequency of the right half plane 0, in this case below 8.68 kHz. For a load change of 2 amperes, the output voltage shall not change more than 100 millivolts, so an output capacitance of more than 366 microfarads is necessary. Keep in mind to combine ceramic and electrolytic capacitors, as this is normally the best compromise between low series resistance and high capacitance. Be aware that the parasitic effects of the output capacitors and their connections get more and more important the more stringent the ripple spec and the step load response spec gets. So relaxed specs for these two parameters reduce cost of the flyback converter. The last but not least component of the flyback power stage is the input capacitor. The input capacitor shall keep the supply voltage stable. A typical value for the maximum ripple allowed on the input is 50 millivolt, which translates in this design to at least 58 microfarads. So 100 microfarads is a good value here. Keep in mind that the input capacitor as well keeps the noise from the source. So when placing the capacitors, place the high-frequency, low-resistance ceramic caps close to the converter power stage. Then they will filter most. In addition, if space is available, spare footprints for capacitors might be helpful. For example, if the conducted noise during EMI measurements needs to be reduced. Now that the power stage of the converter is done, we can go on with the control loop. This is simplest for a non-isolated flyback. The output voltage is sensed through a resistor divider, as in every other non-isolated topology. For the compensation values, have a look to our quick start calculators found on the product page. As this design was done with an auxiliary winding, it could be used for a primary side regulated flyback. At the end, this is a non-isolated flyback with a second isolated winding. The output or load voltage can be calculated based on the winding ratio. This means that the output voltage shows some inaccuracy based on the winding ratios. Here you can see the connection of the regulation signal from the secondary side through an optocoupler to the primary side. For designs with LM5155, the feedback pin is normally grounded, as the reference voltage is necessary on the secondary side. LMV431 is used in this case. The signal transferred from the secondary to the primary is therefore already the failure signal, so the difference from the load voltage to the voltage set by the reference and the resistor divider. Please refer to the quick start calculator for the compensation of the loop and the optocoupler. Other important components for a flyback design are the supply of the controller IC and the components for the startup of the flyback converter. For a controller IC, it is essential that its own supply is as stable as possible. Therefore, a lot ICs have VCC or VDD pins, which need a ceramic capacitor connected to create a stable IC supply. LM5155 needs a 1 microfarad capacitor. Please keep in mind that ceramic caps have DC bias. DC bias means that the capacitance reduces with applied DC voltage. So please use a ceramic capacitor that has a low DC bias. Normally, bigger packages and higher voltage rating means less DC bias. The undervoltage lockout UVLO of a converter makes sure that it turns off when the input voltage is too low and does not turn on at low input voltages. So the design of the UVLO components is important to make sure that the converter only operates when it is safe. See the datasheet or user's guide for these components. Be aware that the soft start or SS in LM5155 changes the feedback voltage reference, so it does not work when the feedback pin is connected to ground. A possible solution is to connect a bipolar transistor from comp to ground that is connected to SS through its base. So the soft start voltage limits the comp voltage and hence the duty cycle at startup. The drawback of this solution is that it is completely independent from the voltage on the secondary side, so overshoots on the output voltage are still possible. A solution to this is the secondary side soft start, as shown on the bottom right. For details on the design of the circuit, please refer to the application note How to implement the soft start in a flyback, shown on the bottom left. In this video, we discussed the second half of the design procedure for a flyback converter with LM5155. The next video will discuss the final step in the design as well as a bit more detailed about the flyback magnetic. The sixth and last video of the series gives some answers to frequently asked questions. You can find further information, for example, in the E2E forum, or ask your question there. A lot of details can be found on the product page, for example, flyback evaluation modules, application notes, models, or design calculators. In addition, a lot of reference designs are available at the Texas Instruments page through this link. Thank you for listening.